Okay, so this week we're gonna get into statistical process control, and we call this SPC in short. So the SPC is you're looking at the process. Okay, what we do is we monitor the variability or dispersion of a process over time. So here you can see the time here, and then of course this is the interested process that you are monitoring. Okay, and our control charts mean like we're looking at the range control chart. So the chart focuses on the range of values. Okay, so here if you look at it carefully, you can see there, here is the row for the range. And of course, there's time. You're looking at the process against time, yeah? And then, of course, there's mean. If you calculate your X bar or the average, it's going to be right here, yeah? And of course, this is our data points. And here you can see your normal distribution here and your data in the histogram format, okay? And you have your upper control limit and then lower control limit, your UCL and then your LCL. So we use this X bar, okay, in our R means range control charts. So we're looking at the range, so you have your average right here, which is your X bar, okay? This is your R bar and this one is your X bar, the mean chart. And we're looking at the process variability. See how far away from the center mean. And of course, that's your central tendency, which is your X bar chart. Okay. So if you look at it very carefully, you're seeing a two normal distribution here. One is on the range, and the other one is on the mean. Okay, so X bar. So this X bar is going to measure the process range. And this R bar is going to measures, okay, the process variability, and that's why we call this R control charts. Yeah, it's a spread in your dispersion to make sure that the consistency and the stability of that process. Okay, we always monitor these process data to make sure that they keep their consistency and stability. Since your R bar represents the average range of the subgroup, you can see how different the histograms are. Your range histogram and your mean histogram, even though we're looking at the same process, the way that we look at it is different, okay? And that's the reason why you have two different shades of your normal distribution. And so this R, okay, chart, so the range control chart focuses on the range of values. So that means the difference between the maximum and the minimum values in the subgroups of the data collected during that process, okay? And don't forget what range is. Range is you get it by subtracting the minimum out of the maximum, okay? Okay, then we'll get into your SPC REN charts. So the REN charts, we use them to monitor the behavior of a process, again, over time. And it's going to help you to detect the trends, the shifts, or the cycles in a process. And what are we going to do? We're going to plot the data points, okay? The data that we collect from the manufacturing or from the factory process, okay? Whatever your interested process data. So these data points are collected, okay? And then we're going to plot that data points in sequence. And because it allows you to observe whether a process is stable or performing as expected, okay? So we're just monitoring our process over time. And SPC REN charts is something that we use to do that. So why do we need to monitor the processes? Because it's very important, so we can detect errors, detect disturbances before they become bad, or disastrous. Of course, in the manufacturing world, your CI, your confidence intervals, are after the fact. The parts are already made, and you're only trying to decide whether to ship them or scrap them, and that's when you use your CIs. SPC is a predictive, method that we use because it detects the problems before. This is very important, before they're out of spec. Spec means specifications here. I'll write it in short so you can make the corrections, of course, before they go bad. Because if things get so bad in manufacturing or production, you have to scrap that product. That's not good. So now you know SPC is really good, and it's predictive. It's also sensitive, far more sensitive of that test than your confidence intervals that we studied before. So SPC usually involves collecting some samples, so that's your data of product. Let's say, like in this example, you have 5 samples, measure some feature, and then calculate the average and the range, and then you're going to plot both your average and range on that graph, right? So our interest is right here, your mean and your range is very, very important. So in the run chart, we have time, we have process data. If you want to put them in a graph, your time is on the x-axis. And let me draw this. Yeah, I don't have to draw it, it's already drawn here. So here, x-axis, and then your y is going to be your data. So this is your y-axis, and then this is your x-axis. So now I drew this for you, so you can see this is your y-axis, and then this is your x-axis. Y, and then your x here. So your time, and then here is your data, and your data points are, look at this, this little green. See that? I'm gonna just write that. Oh, this is your data point, and it's very, very important because you're looking at how far they are from your mean. So over time, since we're looking at the data over time, you can see the patterns of your data variability. And of course, if you see these patterns, you can analyze them and interpret what's going on with that process. So basically, we're using it to identify the process variability. So run charts is going to help you identify the changes, in the process over time. And like sudden shifts in the data, or sudden shifts in the trends, or recurring cycles are all the patterns that we're looking for, in that process. We can also detect non-random patterns. Sometimes you have not very random patterns, meaning like following some rules. Using run rules, you can identify. I'm going to teach you what run rules are. And you can identify non-random patterns like your trends, your shifts, and then and your runs. So your trends are like you're gonna look whether they're sustained increases or decreases, and then your shifts, you're gonna look at your sustained data above or below your median, and then your runs, you're gonna look at whether the frequent up and down movement, what they mean. So these are the things that we're looking at in SPC. Sometimes we also use SPC for baseline monitoring, because it provides you a visual baseline for performance measurement. So it also shows you one process is deviating from, again, your normal operating conditions. So you have to follow normal operating conditions, and then you're gonna run this SPC to take a look at whether they're deviating from that normal operating conditions or not, because the normal operating conditions are very important in the manufacturing factory, and that's how you're making money. So you don't want to go down, so you want to keep the operation in the way you wanted it. Of course, when you find the causes of abnormal variations, we're going to remove them. And that's what we're trying to catch. So by eliminating the problem, variations, that you can go back to your normal, random small variability, it's okay to keep. So just looking at the bad guys and a little bit of variation, that's okay, as long as it's not going so far away from your mean, we can keep it. And we usually keep it in between that upper and lower limit, so you always have the upper and then your medium and then your lower limit. So as long as your process is going up and down in that range, it's okay, Because at this point, control limits, and I just told you about these limits, the upper and your lower limits, your variability patterns, they're pretty much considered normal operation if your data points are within that limits, And if your data points go up and down beyond that limits, like go above the upper limit or go below the lower limit, then that's a very problematic variation, and you need to remove them. Because we collect the data, and every time we collect the data, we want to visualize the patterns and the variations, so we graph them to see it visually on the paper, or on the print, because most of the computer programs are connected to your printer, so you can either watch it, monitor it in your computer, or you can print it out. So every time we catch an abnormal pattern, your immediate action that you need to do is to find out why that is happening, go over to the manufacturing floor and see what's going on. Of course, all of your machines are connected to your data collection point, which is connected to your computer, and that's how we monitor what's going on the shop floor or manufacturing floor, and of course correct whatever is necessary to keep our normal operation conditions. And that's what we do, for the statistical process control. So a lot of people are like, oh, SPC, it's not a big deal. It's pretty easy, and just need to learn how to read the data. Of course, and now you need to know what are the common causes for the variation. So the very first one is your phenomena constantly active within the system. This is just writing it very formally, just telling you that the environment is very active, So things can happen within that system. Of course, all the variations are data, and data, everything that you have to do with data and numbers, and it's also statistic, which is probabilistically, you can predict that variation. Monitoring that variation, you can predict, a condition probabilistically. Sometimes you're gonna have an irregular variation, and of course you're measuring from your historical experience base. Historical meaning, like we call it historic data, all the data that you have ever collected over that process, for many years. And we look at these patterns and understand what's actually going on, because we're using the same process most of the time anyway in the product line. So the irregular variation is another common cause, common cause variations. Another thing is your lack of significance in your high and low values. It's not so very different. Lack of significance meaning it's not very different, in your high and low values. And sometimes you have your inherent in the process. And the next one is definitely not controlled by the operators, because that's most of the variability in the data comes from the process, which is in the system. Inherent mean like the system error, things like that. So here, when you read it, you come to really understand right away. We're just talking about the common cause variability refers to the inherent, your natural variation that's always present in a process, okay? So that type of variability is because of the system itself, and it is considered normal or expected, okay? So when the process is stable and operating under control, and it's really very predictable and usually cannot be eliminated without making fundamental changes to the process. Okay, so that's what we call common cause variability. So it's okay because it is just a system. Okay, the processes off of the system. Okay, in the system. So therefore, you will always have a acceptable variability in that system. Yeah. Like human system, yeah, human system is a soft system because we're made of a biochemical, and we also have a common cause variability inside of us. But we're not the same every day. Even though you have the same body, you feel okay today, sometimes you don't feel okay the next day because of your system, okay, common cause variation happening inside of you. Same as that, okay, manufacturing system. It's not a soft system, but it is mechanical, yeah, and operation system. So there are common cause variation because the system can never be exactly the same from time to time, from second to second. There is variation, yeah. Not a person can be able to do the same process in the same way or in the exact manner. Yeah, you always have a variation. Depends on your system, and it depends on the environment that system is in, kind of like that. So examples are your mechanical tolerances in machine. You have small variations in raw materials. Of course, we're coming back here for manufacturing world, so we're gonna get rid of world example with the human stuff. And also the small variations in ambient conditions such as your temperature, humidity. Okay, so this belongs to the manufacturing world examples. So don't forget, common cause is okay because they're very random, they're predictable, they're stable process, they are inherent to the process itself. Yeah, and you may have like slight variations, small fluctuations, normal wear and tear, your routine human variations in that system. Yeah. So for common cause variability, you don't need to take any kind of action. Yeah. You don't need immediate actions because they're a stable process, and a performance baseline is okay, yeah, in the acceptance level. Then we call that realistic performance expectations and define the control limits, yeah, in your SPC charts. And this one is just an outside example. We're talking about the outcomes of a perfectly balanced roulette wheel. And when you go to a casino, you're gonna see these games, and that is okay. Yeah, a good example of your common cause variation. So common cause variation is just noise within the system, okay, and it's okay. And these variations are acceptable. So this guy, Walter Short, he originally used the term chance cause for common cause variability. So the term common cause was actually coined by Harry Alpert in 1947. So the Western Electric Company used the term natural pattern. Okay, these are the same anyway. So the Short here called a process that features only common cause variation as being in the statistical control. Yeah. So this term is deprecated by some modern statisticians who prefer the phrase stable and predictable. So don't worry about this, is just a little bit of a history. But if you know the common cause variability, meaning like it's okay, system always has variation. A system has one or more processes, and all these processes, okay, they have variations. And these variations are okay as long as they are within the limits, okay? And that's what we're talking about. So a little bit of noise within the system is okay, okay? You don't really need to take immediate action to change that. And that's what we're talking about. It's natural and it's okay, and it is a very much chance cause. It is a common cause, and some people prefer to say like it is stable and it is predictable. Yeah, meaning like we don't have anything that is irregular in this process, and it's a normal. This is just an example of a chart. Now you kind of know how to look at it. Yeah, the X bar your R, and then here is your sum, and here is your data, and then here is the date. The data is taken and we run it on the graph, and you can see the data points right there, and they're within the upper and lower, okay, limits. And you have time, and then you have your data right here, okay, and your range, and then your average. Of course, this is the statistic, meaning the numbers of that data set. Okay, so the data set is here, the number of the data set averages is right there, the mean, your upper, and then your lower is here. Yeah. And of course, for range, the same thing. Range is maximum minus minimum. And you're going to have your upper and also lower, okay, limits for the range as well. Yeah. After common cause, we're going to go into the special cause. Variability is everything that is unexpected, unpredictable, caused by not normal, okay, caused by specific identifiable factors like equipment breakdown, operator errors, human errors, yeah, or certain material shortages that affect the system, manufacturing system. So special causes must be identified and eliminated. You have to eliminate the special cause variation because it's bad, yeah. So by eliminating special cause variations, you can bring the process back to normal or back under control, yeah. So you now know what's a common cause variability. It represents the normal fluctuations, special cause, which is not normal fluctuation but very bad. Yeah. Common cause, you don't have to take immediate action. Special cause, you have to, yeah, do something about it to bring the system or process back to normal operation. So here, of course, I've written in a little bit on formal ways. So special cause variation is characterized by new, unanticipated, emergent, previously neglected phenomena within the system. Variation inherently unpredictable, even, okay, probabilistically. And then your variation outside the historical experience base, something that you don't have, okay, in your historic data set out of it. And evidence of some inherent change in the system or our knowledge of it. So that's just a formal way of writing, okay? So the example is like your tool where then you have your major changes in raw materials or equipment failures, machine part, okay, replacement, over adjustment, unnecessary adjustment, plus your human errors, yeah, operator errors. So now you know special cause variation, they always, okay, these variations always arrive as a surprise. So it is kind of like an alert, okay, alarms or signal within a system. So this guy, of course, Walter A. Short, originally used the term assignable cause, okay? And the term special cause was again coined by W. Edwards Deming. He is very good guy, and he was, of course, he was also very active, okay, in his field, and he went to Japan and did all kinds of quality, you know, training over there. And the reality is, like Japanese, we actually learn, okay, from them, from American, and then we did it very perfectly. So the quality of products in Japan went way over, yeah, Americans' product, and actually because of him, yeah, he brought actually the quality to Japan, and we actually practice it in our products. In America, even though, you know, like one person found a value and method, and he would distribute it, but not every companies in America would follow it, okay? And this is, I think, one reason why the American products quality is not very good, okay? But then, of course, there are many companies like Apple, etc., also follow his, okay, leadership and method again, a method is very important. And that's what you're learning in college, by the way. You're learning methods. You're not just studying college and high school, very, very different. Yeah, high school is like you're copying, but college is you're learning how to do things, okay, methods instead of the subject. So anyway, the Western Electric Company used the term unnatural pattern. So you now know the special cause variation. It's a surprise because it doesn't really happen often in a normal system. So it's kind of like a signal within a system. We call it assignable cause. Okay, we call it special cause, and we call it unnatural pattern. Yeah. And of course, there's an example of that. And look at this, it's kind of weird. Yeah. So you see the special cause variation. And look at this, the upper and lower is not with the solid line, okay? You have to pay attention to these things. The upper and lower limit is not defined here in this chart, okay? So it's only show you there's a dotted meaning line. There is an issue, okay? And of course, the patterns are very, very weird. It isn't like our normal pattern like you saw before, yeah? You can see like how the data are so close to each other, and all of a sudden, okay, go up and down like that. Whereas in the normal process, see, the data are, look at this, they're far away, okay, from one point to another in a very consistent way, yeah. And of course, there is up and down, but not crazy like here. Yeah, here is a pretty crazy. So it means that your process is not in control, okay? It doesn't have consistency. The patterns varies very drastically. So every time we want to monitor a process, so this is what we do for the implementation of your SPC, which is your statistical process control, meaning we're going to use a number of data, yeah? And we're going to look at the process, and we're going to control that process by monitoring it consistently. So first you're going to start and you're going to define the problem, you're going to define the variables, and then you're going to make the sampling plan, meaning we're going to collect the data, yeah? Then of course you collect 20 to 30, so that's your sample, your data. And then you're going to calculate your control limits you needed, yeah? And then of course you're going to get your mean, and then we're going to put that data into R charts. How do we do it? We use application, yeah? Minitab is one of the applications that we use for building SPC run charts. Okay, there are many different charts. Excel, you can do it, but Excel is not good in manufacturing. Yeah, we use a more better or more powerful software like Minitabs. Of course, you monitor it and you apply the rules. I am going to explain, what rules we use, building the R charts by using a statistical software. And then you eliminate the special cause variability, and that is going to come after, okay, this. So we go down that way. And after the rules, we're going to look at whether our process is in control, yes or no. If no, then go back and do the same thing. And if you're in control, then we're going to continue charting the normal process. And you review the chart all the time. So this is what you're doing for monitoring. And then you're going to take the actions on the rule violation if you ever violate the rules that you're following. Okay? So this is what we usually do in the quality control. And my background is in a quality system. So I usually look at the entire system and understand the complexity of the system and the connections, right, or processes in the system, so you can be able to efficiently operate that system. Okay, system engineering is a huge thing. Okay, and quality is one of them. Safety is also another one. Okay, and a lot of the students want to go into the pure engineering line, but you also have to understand there are bigger system operations that you can be able to go into, which you will you will go straight into the management, okay, administration and management line if you follow my path. Yeah, depends on that. Of course, if you want to just stay academic or scholarship like I do, then you can also work at school. I like staying in school because I like to study. Yeah, I don't really follow money, and I don't think money is the only thing, even though it looks that way because the people set that up. Okay, there are many things that we don't understand about this world, and it is for me it's very important to study. Yeah, so I want to keep my life in a scholarship more than finding money and do the worldly thing. So anyways, it's up to you, whatever you want to do in your life. Anyways, the SPC implementation is a very simple one here. Of course, depends on the system. Okay, there will be more complexity, but the normal, right, basic, the foundation is like this for implementation. So now let's get into predictable mean and predictable variation. We're going to take a look at several, right, graphs so you can be able to understand what's going on. So this is the first of your common cause variation, and you can look at this. Your process really pretty. Yeah, it's in control, and these are your subgroups. Yeah, group 1, group 2, 3, 4. Of course, we are using A, B, C, D, but it's the same thing. These are all your subgroups. So you have your A, B, C, D, and it has its own normal, okay, distribution right there, meaning that you are in common cause variation. Your data points, okay, your data points going up and down mean there is variation, but that variation is okay. It is normal. You don't have to do anything. Your time here, and then your data right there. The next one is you have unpredictable mean because it's very different. Look at this. This is predictable, yeah. And here, look at that. The pattern has broken because look at this. Group B, you're shooting out somewhere. So A is okay, kind of. B going out this way, C going out that way, and D is kind of shifted. See that? So meanwhile, the special cause variation is present, so therefore your process is out of control. Okay. If you pay attention, see like how it's so regular here, and see this one like going like weird. Yes, because your range is still doesn't have a lot of variation for the range, but it's kind of, if you actually look at it, the pattern, see, it's just totally different pattern. So pay attention and make sure that you spend, okay, a little time in recognizing these patterns. I go fast because you know, like very you're trained to look at these patterns. And this one is another special cause variation is present. Look at this thing. Yeah, as soon as you see it, you can spot it. Your A is kind of like going taller, and then your B, okay, and then C is bigger and wider, and your D is, of course, kind of okay. So this two of them is very out of control. So your process is definitely out of control. Your range, okay, your range charts also change here in patterns. Well, the next one is your chaos. It is very chaos because look at this. None of them is on the in the same line here. Your timeline is like one is here, there, widened, and this is smaller and that's wider. And here B is shooting out that way and D is off. Yeah, on this side. So this is a very bad process and behavior because the process is definitely out of control. So you have your special cause variation is present in this, and it's very chaotic in the system. So let's take a look at the relation to customer or product specifications. So we have 1, 2, and then 3 and 4. And number 1 is in control. See like how pretty and consistent, and is capable of meeting performance. Number 2 is in control, but look at this. Yeah, your normal distribution, it got wider here, so it's not capable of meeting the performance. But performance, our goal is like this, but here our current process, like this, so it's not acceptable, but still in control. And number 3 is not in control because look at this, how they're shifted up and down like that. So currently, it does meet the specification because it is still within the upper and lower, Look at this. Here, number 2 is wider meaning like the upper and lower limit. See, there's a violation, meaning like going your data points above the upper and below the lower, okay, limits. Here, the process is not in control because it's shifted like that, but it's still inside on the upper and lower, okay, limits. So you're still meeting the specification, but it's not that good. Here is it doesn't meet the specification. Also, it isn't in control. Yeah, see, it's very chaotic. Make sure you train your eyes to be able to see. Yeah, you have your mean, and you have your upper, and you have your lower. Yeah. And you will play with that. You have 4 different categories here that you need to understand for the process in control, the process meeting the performance or not, the process in control or not. Okay. Then we'll get into run rules. So we have run charts. So in order for us to build the run charts by using statistical software, you have run rules. Of course, you can build these charts by using, I told you, one software, Minitab. You have SPSS, okay? Another one, you also have like a JASP, you have PSPP, you have JMP. You also have, all kinds of, you also have Excel, but Excel is not that good, yeah? Than other powerful software. But anyway, so, since you have a student email, you can be able to download these softwares, yeah? Sometimes free and sometimes just pay a little bit of a student price. It's not much, yeah? So anyway, so let's get back into run rules. So run rules are established and used to examine your X bar, okay, and then your R range charts, and determine whether the variation normal background common cause variation or their special cause variation, yeah? Because you have to make sure that you understand the difference between the common cause variation and special cause variation, and you should be able to spot, okay, these variations on the graph that you draw. Special cause, something bad happened, and we're about to make scrap, okay, we have to eliminate something. Common cause is okay, it's in normal, yeah, conditions. So that too, you need to know the difference between them. So run rules, we use it to find a violation, okay? So if we catch a pattern and then we decide whether we violate, okay, we violate something, then we check up against these rules, yeah? And we have to decide if we did violate something, then we have to decide what to do. So we're going to examine the X bar, and then we're going to examine the R charts, okay? And if there are no violation, we say the process is okay and is in control. So if we see violations in the X bar, R charts, okay, like this, we say the process is out of control, meaning something unusual has happened, and we are either making scrap or about to make scrap, and we have to do something about it, okay? So here, when you look at it, oh, not normal, something very unusual is happening here in this chart. Yeah, you can look at these weird patterns right here, and that means it indicates violations of something, okay? So therefore, we have to do something about it. All right, the rules. Very first one, outliers. So outliers is any data point, okay, that falls outside the control limit. So here you can see the upper limit is right here, and you've got a one outlier, okay, which is above your upper control limits. And here, look at this, another one below the lower control limits, and these are called outliers. And the distance we measure by using sigma value. So this is your mean, and this is the very first sigma, second, and then the third sigma. 1, 2, and then 3 sigma. And if your data is okay outside of the third sigma, that's not good. Yeah. So we have plus, you have minus, plus mean upper, and then minus mean lower limit. Okay. The standard deviation 1, standard 2, standard, and 3 standard deviations. From where? From your mean. Okay. This is where our measure line is. So that's your mean. We measure from the mean. We're measuring what? We're measuring the data point. And this guy is okay, below the second standard deviation. Okay, this is your first standard deviation. So it's between the first and second standard deviations, and it's away from this x bar. Okay, that guy is right at the middle, yeah, x bar, and this guy is about one standard deviation away. This one standard, and this one about 2 standard deviation away, and this is lower than 1 standard deviation away. Okay, so this is how we measure the distance from the mean. Okay, and you can see the distance are carefully divided. Of course, they're equal distance because you go like that. So 1 sigma, 2 sigma, and 3 sigma. Yeah. So every time we have an outlier, we have to investigate the process because it is statistically more likely that there is an assignable cause, causing a change in that process. So if no assignable cause is identified, then we could believe that this was due to random chance. Okay. But right now we do have the outlier, so we gotta do something about it. Yeah. The statistical probability that a sample, your data point is a sample. So this is your sample mean, okay, from the same process falls outside the limit, okay. It's usually like this, okay, outside the limits. It's about 0.3%, okay. Not much, but it can happen, yeah. All right, number 2. The second run rule is your shift of mean to 7 consecutive points on same side of mean. So when you look at it, look at this, we have only 1 data, 2 data, and 3 data on this side, meaning the negative side, which is lower. Okay, control limit, look at the upper control limit between x bar and the upper limit. You have so many data points, and we count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And here are 1, 2, 3, 4, 5, 6, 7, and then 8, 9. Okay, look at that. So that's the 7 consecutive points on the same side of the mean. It's no good. Okay, that's a violation of your random rule. So it's statistically unlikely, and that your random process will have like a 7 means on the same side. So this is an indication that the process mean may have shifted up or down. So meaning you're getting the mean wrong place. It's got to be around here. So when this potential shift is observed, then the process must be analyzed to see if that mean has shifted. Okay, meaning like if this is a true mean or not. Yeah, and if it has, then we either have to fix the problem or possibly calculate new control limits. Okay, if we're gonna run with the same with a new mean or with the same mean, because same mean you can run it, because this is not a very good data. Okay, not a very good process. So therefore you have to come up with a new mean, or you have to analyze if this mean is a bad mean, meaning like it's got shifted from where it's supposed to be. Yeah, so these are the things that we do every time we observe more 7 data on the same site. Number 3, the run of 7 increasing or decreasing. Okay, so if you have a run, so look at this, it's going down 3, going up 1, going down 1, and then going 1, 2, 3, 4, 5, 6, and 7, going up 7. See, it's a 7 increasing. That's not very good. So it is statistically again unlikely that a random process would have produced 7 consecutive sample means in an increasing or in a decreasing manner or relation. Of course, this example is showing you is going up 7 data increasing. So this is an indication that your process mean may be undergoing a shift. So meaning like this is not a good mean. It must have been shifted. It's got to be somewhere around here. So this is cause for concern, even though no points are outside the control limit, because continuing of this trend will cause out of control points. So if more than 7 consecutive points are increasing or decreasing, the 7th point, this guy here, and all subsequent points, we're going to consider that out of control. So these are the data points that are out of control. So when this potential shift is observed, then your process must be analyzed. You have to take a look at the process. You don't just leave it as bad. So you have to go in there. If you're in the management, you're gonna go in there and check what's going on to see if the mean has shifted. Check, okay? And then if it has, then you have to fix that problem, or possibly you will calculate a new control limit, okay? If we're going to run with a new mean or do something about it again. All right, the next one. All right, the next one is grouping. So groups are consecutive points that are close together, okay? So you have, when you look at it, you have like groups, okay? Here, a cycle is different, okay? When you look at this cycle, look at this pattern, you need to know how to look at them. This is in group, yeah, it isn't in cycle. So for a cycle, there's no set number of points required to define grouping. It is merely a point at which the data does not appear random. So here you can see the cycle. The data, it isn't random, yeah, because there's a distinct pattern of cycle there. And here, groups, it's just a consecutive points, okay, and they're close together. So see this little group, because these points are close together. This one too, see, these points are close together. So make sure that you understand how to see the cycle pattern and group patterns. So example causes of grouping may include your variations, yeah, from operator to operator, or variations of your raw materials like that. So if there are many groups present and these groups have a cycle pattern, then they might also by a cycle causing, right, the out of control, so such as operators on different shifts. So these are the things that can cause the group, okay, groupings of your data points. So every time you see grouping of the data points, that's the indication that you need to go and take a look at your process, okay, and do something to get your process back into control. All right, the next one, instability. So how are you going to spot instability? You're going to look at your data. You know, if your data has like extreme highs and then extreme lows, then you have some instability, okay? So any specific data point may not be out of the control limits. They're not out of the control limit, they're inside. We don't see any outliers here, but it is statistically unlikely that the data would randomly be very high or very low at frequent occurrence, right? So here going up and then down, and go up and then down. So it isn't very good data because they're going up and down, okay, frequent like that, even though they're within the upper and lower limits, okay? So approximately 2/3 of the random data should be within plus or minus, okay, 1 standard deviation of the mean. So when you look at it within the 1 standard deviation, okay, this is plus side and that's a minus side. You see we have only 1, 2, 3, 4 data out of all of this data, okay, so that's not in 2/3, yeah. Actually you have 4, yeah. So 4 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 4 by 14. So 2 by 3 is 0.6, 4 by 14 is 0.28. So it's not good, yeah? So that's how you identify the instability. Now we come into less frequently used rules, and here they are. So 14 more points in a row alternate in direction increasing then decreasing. So if you have like a 14, okay, 14 points like this, you count them out and there's a total of 14 points. And they're in a row alternate, so meaning like going, okay, this down and then down here, up and then up, down. So they're going row alternatively in direction. So going up and down, and then increasing and decreasing, going like this. Okay, it's definitely not random data. And sometimes you have like a 15 points in a row, okay, are like within just 1 standard deviation, okay, of the mean. Is not good either, okay, because your data is supposed to spread of 3 standard deviations, okay, on each side, and we call that the Six Sigma, yeah. 4, of course, here 4 or 5 out of 5 points, yeah. So when you look at it, 1, 2, 3, 4, and then out of 5 points, 4 of them, okay, 4 of them out of 5 points in a row are more than 1 standard deviation. So when you look at it, this is your first, okay, standard deviation. So 1, 2, 3, 4 of them are more than 1 standard deviation. That's not good either, yeah. So you will spot when you're monitoring your process, or you're trying to pay attention to these. Okay, all these are 7, and then of course less frequently used. So you have 6 here, and then 7, 8, and 9, about 9 rules, yeah, to look at the different patterns, so you can be able to monitor if you and decide whether your process is in control or not. If it isn't, you're gonna go and take a look at it, yeah, and do something about it. Alright, so what action do you take? Continue to run indefinitely, but watch your process very closely, and you're going to ask questions of operators and all the experts, okay? You can't decide by yourself. You always have to work with your team, and every time you do a decision, don't just go ahead and do it by yourself. Yeah, always go into meeting, talk to other people, talk to expert, talk to everybody, okay, related to the process that you're monitoring, and make the decision. Okay, continue to run just long enough to gather more data. Meaning, like, you just have to continue to run the process, okay, but then don't run, okay, too long. Just run just long enough to gather more data points, so you can be able to do a good decision. And then you're going to continue to run, but only to troubleshoot, okay. You don't have to like run a long time, just enough to gather more data, just enough to do your troubleshooting. And then you're going to shut down immediately, and then troubleshoot. That's things that you can do, yeah. You can run again when you think you have identified, eliminated, assignable course, and monitor your process. Okay, so if you ever found violation of these rules, then you're going to repeat this, okay, and do one of this. Alright, well, that's it for your SPC. You know, I have uploaded your Excel, okay, how to process your data. I gave you plenty of examples, yeah, in there that you can review your Excel. And yeah, that's it for this week.